Good day. My name is Cheila Avalon Cullen. I am a physical scientist and an assistant professor of Earth and Environmental Sciences at the City University of New York. Today, I would like to tell you about how we used the Climate Hazard Group Infrared Precipitation with Stations dataset, known as CHIRPS, to derive a landslide numerical factor for shallow rainfall-triggered landslides. For that, I would like to locate us in the country of Colombia in South America, with its very complicated tectonic settings, which give rise to the amazing Colombian Andes. In this area, tough terrains with steep slopes dominate the landscape and create various regions. The Colombian Andean mountains have only 33% of the landmass of the country, but contain at least 78% of the national population. Also, given the interesting tropical rainfall regimen of the country, the Andean region is also presents 92.5% of the total reports of landslides in the country, where at least 92% of those reports are landslides that were triggered by rainfall. Now, the focus of this research is to model the conditions that led to shallow rainfall-triggered landslides in Colombia. This type of landslides are caused because of changes in the shear strength of the soil. They are considered to be shallow, and they are codependent in the interaction of hydrological and mechanical processes, which drives us to consider the analysis of these two types of factors. But we encounter that although various studies around the world have been successful in determining rainfall thresholds via satellite information, the tropics are a whole different story. That is because dense vegetation and complicated terrains prevent the instruments from retrieving reliable data. For example, while conducting exploratory research, we did not find reliable satellite-based antecedent soil moisture information. And as you know, soil moisture is pivotal for the study of rainfall-triggered landslides. And perhaps, we believe, this is the reason why various physical and not satellite-based rainfall thresholds have been determined for the Colombian region so far. Therefore, we looked for a system that could help overcome this challenge. Enter CHIRPS. CHIRPS builds on various thermal infrared precipitation products, such as the TRMM Multi-Satellite Precipitation Analysis version 7, and it uses various interpolated gauge products as well. CHIRPS was developed by the United States Geological Survey and the Climate Hazard Group at Santa Barbara, California. But what is most important for this work is that CHIRPS has been validated for Colombia, where at least 338 rain gauges from the Colombian Institute of Hydrology and Meteorology, IDM, were used to compare to CHIRPS. So, let's take a look at how we developed this process. First, we started with a rainfall-triggered landslide database of about 346 landslides that occurred in the country between the year 2016 and 2019. Now, what is important to highlight about this inventory is that the date of the event was recorded, but not the time at which it happened. That is very common for this type of landslide inventories. Also, for the basis of this analysis, there were many assumptions that were undertaken. One of them being that we assume that the soil moisture content for a specific location is dependent on the amount of and duration of rainfall that occurs before the landslide event and on the known rain or dry periods between rainfall episodes. So by following the successive rainfall dry periods, we can characterize how much moisture is left in the soil directly before the landslide. So here in the screen, you can see the logical workflow where PR1 represents the number of days of that very first rainfall. RS1 represents the total amount of rain that fell during that episode. DT represents the dry days between the first rainfall, and PR2, which represents the second rainfall, with RS2 that represents the total amount of rainfall of that detonating rainfall episode. This can be seen more intuitively by using an example. So here we see the rainfall characteristics for two successive rainfall dry periods at one location. PR1 and RS1 represent the very first rainfall recorded at that one location, where PR1 is the number of days that the rainfall lasted, whether it was intermittent or not, but it accounts for the 24 hours of that day. And RS1 represents the total amount of rainfall in that period. Then in this particular example, there was no rain for 2 days, but later it rained for another extra day. And that was the rainfall that triggered the event. Now, these rainfall dry pairs start at the beginning of the rainfall time series, which for us is January 1st, 2016, until the time of the landslide, as it is listed in the inventory. Each pair is stored as a running data line where PR2 and RS2 become PR1 and RS1 of the following line. So at this point, when having modeled these rain and dry periods, we can then relate them into one single factor that represents the moisture content in the soil before the landslide event, and it is deemed as the first landslide triggering condition, PMC. Also, we can express that one triggering rainfall episode and represent it as the rainfall sum trigger, RST quantity. Consequently, we can integrate these two activating parameters into a single parameter, which we call the landslide triggering factor, LTF. And then we normalize it by the slope. Of course, under the assumption that as the slope increases, the amount of rainfall necessary to trigger a landslide event will decrease, and vice versa. In this manner, the LTF simply describes the relationship between the expected antecedent moisture content in the soil, which is represented by PMC, and the rainfall, RST, that according to the landslide inventory, triggered that event. Consequently, we divide the dataset into a training and a testing group. We then ran the equation that you see in the screen at each landslide event, all the way from January 1st, 2016 to December 1st, 2019. And then we realized that the LTF values that are associated with an actual landslide event can be set as thresholds for the corresponding slope angles. And we see that that relationship between the LTF and the slope angle follows the equation that you see in the screen with a determination coefficient of about 0.84. Here we can see that the LTF slope relation rapidly changes in the smaller slope angles, while it barely fluctuates in the large ones. We notice that the LTF slope relationship is congruent with the physical mechanisms that drive rainfall trigger landslides, because physically, A rainfall trigger landslide develops as the moisture content of the soil and its pore pressure increases. The slope fails when the driving force along the slip failure is greater than the shear strength of the material and its cohesion. In steep slope angles, the weight of the soil along the slope surface is already significant. And in this case, a small amount of additional water weight is likely to initiate a failure. This explains the low variation of the LTF in the high slope ranges. And well, although these findings are very interesting, we could not just stop there because we needed to compare this to something that has been already very well established. So we compare the LTF threshold to the event duration rainfall threshold. This ED threshold uses the duration and accumulation of the triggering rainfall to establish a level that, once exceeded, will lead to a landslide event. When we compare the LTF method to the ED, it is important to highlight that the LTF not only considers the triggering rainfall, but also it evaluates the effects of the preceding precipitation before that one triggering rain, and also the dry period between the two rainfalls. And when we look at both the training and the testing data sets, we find that the LTF threshold performs better than the ED threshold for 71% and 81% of the cases, respectively. We think that the difference in performance between the two thresholds can potentially be explained by the introduction of the parameters that simulate the state of the soil before the landslide event, and by relating them to the slope inclination. Mind you that the LTF method considers 5 dynamic variables: RS1, PR1, RS2, PR2, and DT that precariously, but they try to simulate the wet state of the soil before the landslide event happens. Well, but how does this threshold help us in real life? Well, the LTF threshold can then be modified to be applied to a dynamic hazard map. So here we modify the LTF equation to the dynamic map equation, where quantities represent the average rainfall in millimeters per day for the two rainfalls and the corresponding slope. So in the figure that you see in the screen, it is anticipated that when the DM quantity exceeds the LTF threshold, a landslide should be expected. Results demonstrate that areas located in the mountainous areas region of the Andes show relative low DM values that are necessary to trigger a landslide. This is evident since the area is characterized by high slopes, and conversely, areas located in the lowland regions with gently or very low slopes require higher DM values. So with the various assumptions that we have discussed here today, we developed a satellite-based threshold value that characterizes what happens in the soil before the rainfall that triggered the landslide happened. We did this because accurate satellite-based antecedent soil moisture for the tropics is very hard to come by. And when we compare our results to the ED threshold, we see that the LTF does perform better for both the training and the testing data sets. Well, with all that said, thank you so much for your undivided attention. We invite you to read the details of this work in the Journal of Remote Sensing. and also to share your questions, opinions, or queries with the conference coordinators who have our email address so we can be in touch. Thank you again, and be well.